start with radioactivity, okay? And what we do is we are going to just look into this diagram which we have seen a number of times. If you take up any nuclear physics book, uh, be it Ghoshal or any other book, okay, you basically get this diagram there, okay, and then I think I have told you this again and again that when you have the number of protons and neutrons equal, this is nothing but n by p ratio, which is 1. So this basically is the straight line, which is the stability region. The question does arise that are there any neutron proton combination which lies on this line? The answer is yes, okay, because if you consider something like helium, which actually is the beginning, okay, of something which is more stable, because if you look into the binding energy per nucleon curve, which you're going to see later, we do see that helium actually shows a peak. So that means it's more stable. But if you consider the configuration, it is 4 2 helium. So that means there are 2 protons and 2 neutrons. So any graphical representation gives us a clear picture. So if you go 2 2, that means it will be somewhere here, right? It is somewhere here. So it's 2, okay, then this is 10, so obviously this is 2 2, so it's somewhere here. So there are few elements which lie on this line, but these elements are actually only up to a lower atomic number. So you can see, if you consider up to this particular point, it's somewhere near 20, right? It is somewhere near 20. So if you consider something like in the periodic table, if you consider something like let's say even the nitrogen, okay, 14, so it is 7 7, okay, and so on. So we have number of protons and neutrons equal, and they are valid only for less number of less mass number, okay, the A value should be low. But as we go to higher and higher mass number, it diverges from this straight line. So does it mean it is becoming unstable? The answer is no, because we have a number of reasons. So that can be a descriptive question. You have to understand nuclear physics and then only you need to answer. Probably you can take semi-empirical mass formulas logic and try to answer this question. So the question would be, if we divert from n is equal to p value, okay, does the nuclear become unstable? The answer is no, because for a lot of nuclei there are more number of neutrons compared to number of protons, but they still stable, okay. So this region, the dotted lines, okay, whatever you can see, are actually the actual number of neutrons and protons, and they are basically called the band of stability. Now, if we have, let's say, if this is the band of stability, doesn't mean that all the element will lie in this band. Some element might lie on this line, this side of the band, on this side of the band. Some element might lie on this side of the band. So if it lies either on this side or this side, this won't be stable. It will be unstable. Okay. So if it wants to become stable, it will emit radioactive rays like alpha ray, beta ray, gamma ray. Okay. So you have already known this, but this is from a graphical point of view, which might be more important. Okay, because we have upgraded ourselves to understand it better. So if you go to any region, let's say let's consider silver, okay, we have 47 number of protons, and then the remaining is neutron, okay, so that's 50, okay, 50, 47, 60, so 60 number of neutrons and 47 number of protons, and if you take the ratio, it becomes 1 by 2, 1.28. So you see a ratio of 1.28, it starts, and then up to maximum it goes up to 1.51. So if the ratio doesn't go beyond 1.51, please remember this, okay? This might be a part where I can ask you a tricky question. If the ratio doesn't go beyond 1.51, that the nuclei will be more or less stable, okay? But then if it goes beyond this, see, lead is not the ultimate element. You have elements after that, right? You have other radioactive element, let's say plutonium or uranium and all, or thorium. All of them has got a greater value of A, not 206. They are much more than that. So that is they are unstable. So that means if the N by P ratio becomes one more than 1.51, that means neutron is more than proton, right? It becomes more than that, then that is actually nothing but unstable. So please remember this, why it is unstable. Okay, so that becomes unstable. So radioactive isotopes are outside the band of stability. So if you consider this as the band of stability, okay, this entire region, and if you consider the radioactive isotopes just like uranium, thorium, plutonium, and so on, they won't be in this band. Okay, they will be outside this band. Okay, so they will be outside this band. So if you consider, let's say, uranium, right, 92, so you see in this stability band it can't even be plotted. Okay, this is not shown, but you can always plot it. It will be lying somewhere here, okay, because we do have the number of protons and neutrons, right? So it is 92, and if you take 235 uranium, it will be 92 minus 235. Okay, so it will be approximately 140 something, right? So it will be somewhere here. It will be somewhere here. So that is not there in this band, but obviously it exists. Okay, so this is outside the band of stability, and what happens is they will undergo nuclear reactions to become more stable. Now, do I make the reaction man-made or it is natural? Depends on how unstable it is. Most of the times it will actually continuously emit alpha ray, gamma ray, beta ray, and then it will try to come to a stable state. Okay, so that means if it's here, it tries to approach this part. It tries to come here, tries to approach here. So this is what is graphically more important. So in general, it has been seen that if we have the number of protons greater than 83, they are more or less radioactive. So you see up to lead it is 82, and beyond lead, if you consider the number of protons, we have 83, they are we can say radioactive. But then if you consider something as radioactive, there are different isotopes, and some isotopes are more unstable compared to some other isotope because of obvious reasons, right? Because half-life would be more, so it is more stable. So in the next lecture, we are also going to see half-life. Okay? So when we discuss half-life, I think that will be much more clear, but we are going to revisit this idea again and again. Okay? It's very simple. So then I think this is something which most of the time it is not discussed, but I think we can discuss this. As you all know, I am not very good with chemistry, so I cannot name all the elements. Probably you can name all the elements better. But let me just tell you, if you look into the periodic table and you have the group and the periods in there, okay, you have the groups, okay, you have the groups and you have the periods here. And then when you look into it, you see that the radioactive elements are there. Okay, so you can see that, as I said, greater than 82. Okay, so it is 84, 85, 86. But some element like this, okay, Tc, okay, this will basically have 43, but it's still sometimes radioactive because it is unstable. Okay, it is unstable. So this is also radioactive in nature. This is a unique case. There are always general cases, and then apart from that, you can also consider PM. Okay, so this is also having a value of 61. So this is also unstable. But then apart from that, all the others will behave normally because they have got more number of neutrons compared to protons. They become more and more unstable. Okay, and then they will radiate. So this is there. Okay, and this is very important, I think. And if you just go through this, this is something which is mostly explode uranium. Okay, U-292, which is actually important for our purpose. Okay, so there are some more elements like, let's say, actinium, okay, and or thorium, okay, or even palladium. Okay, so let me tell you, some lab experiments are also done using palladium, and palladium is actually radioactive. Okay, but then for using palladium, they are used in the stable state. Okay, room temperature stable state. So we don't want to make it much unstable. We also have polonium, okay, which is also there, uh, which is radioactive in nature. Okay, so carrying out experiment with these kind of elements has to be very careful. Okay, it needs to be taken with extreme care. Don't worry, this is not for your exam. You don't need to really remember what are the elements which are radioactive. I will totally omit this. I don't think this doesn't make sense to remember so many things. But I think this is okay. Okay, at least we know that you can look into the series. Okay, the lanthanum series. It has got some radioactive element. Okay, and the last period of the periodic table is more of radioactive in nature. So just a general overview, I think it will always be good. So basically, when we talk about a radioactive element, they usually don't have any stable isotope. They are the elements which exist in the periodic table, but do not have a stable isotope. Okay, so that's important. So we will actually see more of this, but only in terms of uranium. So then, if you consider sources of radioactivity, what are the different types of radioactive elements, okay, or radionuclide, as we say? So there are three categories. The first category is primordial radionuclides. So something which is primordial means it's very old. Okay, so that means that is something which exists from the origin. So when Earth was created, these elements were already there. Okay, and then there were some elements which came up, which was actually later. So when the Earth was came into existence, some of these radioactive elements which was created had a very long half-life. So we are going to discuss about half-life in the next lecture, where we are also going to do some numerical. But I think what I can say here is that uh, the important part here would be like if we consider the half-life and if we say that the half-life is short, that means the nuclei will become stable at a very fast pace, so it becomes more difficult to study that. Okay, so when we go into this concept of carbon dating and all, we what we know is that we can actually find out the age of something which is very ancient. Okay, because carbon has got a very long half life, so definitely it's going to exist for a longer period in that particular material. Let it be a tree or something. You want to determine what is the age of a tree, you basically use carbon 14 dating, right? This is radioactive, but then the half-life is very long, so it will actually have its existence since eternity. Okay, it's a very long time. But when we have a very long half-life, that means these elements are still present on the Earth's crust. Okay, and because of some reason or the other, they are recreated. So uh, Pb, Ra, even potassium is radioactive. Okay, so elements are there, then that is where we actually use it. Okay, so if you consider something like lead, of course lead is stable, Pb is stable, but then it is radioactive. Okay, it is radioactive, it still emits some kind of radiation. Okay, then we have got something which is called as the cosmogenic radionuclide. Now, cosmogenic radionuclide is something which actually is present in the or produced, in fact. Okay, in fact, manufactured in the upper atmosphere. Okay, it's all nature. Okay, it's all nature. Okay, we have nothing to do with man-made radioactive element till now. We have it after this now. In the upper atmosphere, we basically have it, and these are actually nothing but a result of cosmic ray interaction with light particles. Okay, so what happens is cosmic rays, are highly energetic particles, and then they are actually able to interact with the particles which are present in the atmosphere. For example, carbon, nitrogen, oxygen. Okay, so when they basically interact with it, they basically have formation of some radionuclide. Okay, which is carbon 14 is also one of them. Okay, beryllium, sodium, phosphorus, sulfur. Okay, so these all are radioactive, but then they are not as dangerous as the nuclides that we basically call radioactive, like uranium and all, because they emit a very high intensity of radiation, but these doesn't usually give the high intensity of radiation. So we do have doubts sometimes that carbon 14 we use for radioactive dating, but is carbon 14 radioactive? Yes, it is radioactive. Okay, so I think this is clear now. This is comes under the category of cosmogenic radionuclide. And then we have got the anthropogenic radionuclide. These are actually nothing but man-made. Okay, so there is sometimes like some of these radioactive elements are actually discovered accidentally also. What happens is there are a lot of man-made activities like nuclear fuel fabrication and all, enrichment and all. All the elements listed in the periodic table are not something which are natural. There are many man-made elements, okay, which are actually used for different purposes, but then they exist now. Okay, we have it. Okay, we can actually make it. Initially there was also cases where people used to have this ores. Okay, ores of different elements, but then there was a mixture of element present, so you have to do some processing to actually divide all the elements, and you find out new elements actually present in the Earth's crust. In a similar way, when nuclear reactions are carried out, nuclear fuel fabrication, okay, nuclear power plants and all, I think we have already studied about these things. Enrichment, okay. So whenever there is here, or even nuclear accidents, okay, they actually give out some kind of radiation which actually man discovers. Okay, so something like cesium. Okay, cesium, there are two isotopes you can see, 134, 137. Both the isotopes are actually man-made. Okay, so it might not be intentional, it might be because of an accident, but it's there. Even iodine, okay, iodine is there. Okay, Sr is there, I think it's strontium. Okay, and more and more. Okay, so these are all nothing but man-made. And then see, the list is not exhaustive. There are a lot of elements in the periodic table in the which are radioactive. Okay, but then I have not given this, like carbon 14 has not been highlighted in that periodic table, because we are considering only the main elements which are present in the periodic table which are naturally radioactive. Okay, so these are also naturally radioactive, but then the intensity is very low. And I've not listed all. Uranium also comes under the primordial radionuclide, because this is actually present in the Earth's crust. Okay, it's there. So it's the presence is always there. Okay, So we have something which we call as the alpha decay, and we already know about these things. But then let's just look into it, just revise it a bit. We have release of two protons and two neutrons, which makes the nuclei from which it is released more stable. This helium reaction is also one of the reason in the sun because of which energy is created. So you know that basically helium is associated with a large amount of energy. Okay, so this is equivalent to a helium nuclei, and then it has got a charge of 2 plus because of the obvious two protons that we have, and then mass is 4 AMU. Okay, atomic mass unit. Just convert the unit, you can get the value. So in MeV. So this is actually the largest and of course the slowest, because as I have shown you in the image day before yesterday in the last class, that if you use your hand, you can actually stop an alpha particle. Okay, it's possible because it cannot penetrate that much of depth. Okay, even with a piece of paper it can be stopped. Okay, so it has got less penetration power, and then it changes to a different element with a lower atomic mass and lower atomic number. So whichever element actually emits alpha particle, which actually change the element altogether. So if uranium or thorium or plutonium keeps on emitting alpha particle again and again, finally it is going to come down to a state where it will be more stable, like lead. Okay, so lead will be more or less stable. Okay, it will exist as lead only. Okay, it's not going to change its state. So we have got polonium, which is having atomic number of 212. So we have got, sorry, the mass number of 212, atomic number 84. It will basically get converted to lead. Okay, so in general they do ask you some examples. Okay, this might not be a question which I will ask you in exam, but you know sometimes in entrance exam they go with the simple questions also. So it's very important that you all are clear with the concept. Okay, so if you consider something like uh, okay, so plutonium, right? So we have it, and then it will emit an alpha particle, and then we can actually get uranium 236, and then it will again emit, it will go to some other state, and so on. Okay, so it keeps on happening. So this is exactly what is alpha decay is all about. And then beta decay, I don't think I need to give any sentences there. In beta decay there are two decays. One is the beta minus decay. Okay, beta particle emitted will be nothing but electron, and the other one is the beta plus decay. So that means the beta particle emitted will be nothing but the positron. Okay, so we have to remember these two because this is important, because this is slightly tricky. What happens is when an electron is getting emitted, it effectively creates a hole. So in order to keep this neutral, the positive charge should increase by 1, right? So this positive charge should increase by 1 when electron is emitted, because when electron is emitted, it is equivalent to a presence of a positive charge within the atom, right? So within the nucleus. So we can just say that this is 55 will become 56. So that means if electron is emitted, the atomic number will increase by 1, so it will become 56. Okay, the mass number will remain the same, 137. So that's basically becomes barium. So this is just an example, cesium getting converted to barium. Okay, so this is important, so try to remember this. Okay, so next we have got this. Okay, so what happens here is basically a neutron will get converted to a proton with the emission of an electron. Okay, so you can take this as an example, but we are going to go more deep into it later. Next we have got sodium, and if you consider sodium, and then let's consider a beta decay there, and let's say there is a positron decay. Okay, so this reaction actually happens, possible. Okay, so what happens is if there is a beta particle emitted, which is positron, this will actually be equivalent to a electron, or if a positron comes out, there is a presence of negative charge there, because negative charge will keep on hopping from one region to another. So in order to keep it neutral, this has to reduce by 1. Okay, so this will become 10, otherwise this will become an ion, right? So this is 10, and then this is 22. So please remember this. Okay, because this is important. Whenever there is a beta minus decay, we increase the atomic number by 1, mass number remains same. When there is a positron decay, we decrease the atomic number by 1 and mass number remains the same. Okay, so beta decay is not simply electron emission, it may be electron or positron. So that's why this slide is important. And then of course radiation, well, practically gamma doesn't have any mass, so it will have maximum penetrating power, because you know if there is more mass, the chances of it getting stopped is much more simple, right? But then if it is doesn't have mass, it travels at a relativistic speed. Okay, the speed will be comparable to the speed of light, it becomes more difficult to stop. So this is usually not a particle, and then the electromagnetic wave with a short wavelength, it has got a very short wavelength, it has got a very high frequency and energy. Okay, so what happens is this wavelength is low, okay, very low. So that means if you just consider a gamma particle, something like this, right? Very very short, very short.
Sir,
Yeah.
sir, beta decay is of two types or three
Hmm.
types, like a beta minus, beta plus, or one is one electron capture is there, na?
Yeah, but
So
that
that
is a
will be
different. Yeah, but that is there. But the thing is, the electron capture part doesn't come under radioactivity. Okay, so
okay.
so we will check that. But then beta plus and minus decay are something which is usually
Type.
observed. Okay, when we talk about radioactivity.
Okay.
So what happens here is we are basically going to see the wavelength, and then we said that the wavelength is actually very short. But when we consider something like, let's say, electron, okay, the waves emitted by an electron or by an alpha particle, this will be much larger. Okay. So if the wavelength is short, of course the frequency is high, because definitely we know they are inversely proportional, and E is equal to h nu, so E will also be high. So I think this is important, because whenever you are asked any tricky question, these kind of ideas will be more clear. And of course they don't have any mass or any charge, so that means they will actually practically be more energetic. Okay, they will have more energy, very very fast, travels very fast at the speed of light. So whenever we are saying it moves at the speed of light, so it is comparable to the speed of light, that means that you are considering something which is relativistic in nature. So if you go into the physics of this, try to derive a relation, we definitely need to consider speed of light. And then this is of course stronger than X-ray. Okay, it is stronger than X-ray, definitely, because you know, X-rays are also radiations, but they can actually be stopped by bone and all. But gamma radiation are even more energetic than that. Okay, we have to do some calculation to actually find out what is the energy that is with X-ray and then with gamma ray. These are two different things. Stopped by several centimeters of lead. So you need lead, as I said the other day, when you do a nuclear experiment, the lead and all is very dense. Even the concrete construction that are done, the dome, the nuclear dome that is being constructed on top of a nuclear power plant and all, the construction is slightly different. It's not the conventional construction we do for homes. They are also using cement and concrete structures, but then they are more compact and uh, efficient in stopping the nuclear radiation to pass through. So whenever we say nuclear radiation, the target is to stop gamma radiation, because if gamma radiation can be stopped, obviously alpha and beta radiation can be stopped easily, right? So this is something which we have seen the other class also, last class. If we have an alpha particle, it can be stopped by a piece of paper. If you have a beta particle, you can stop it by aluminum. Okay, even an aluminum foil can stop it, a beta particle. But then if you need a gamma ray to be stopped, you definitely need some lead or concrete. Okay, so that is very important.